Today we're going to talk about limits. Now, a limit is a major concept that bridges all the math you learned before calculus to all the math you're going to learn at calculus. We apply limits to basic ideas such as slope of a line and area of a rectangle, and we get these fundamental ideas of calculus that we're going to learn throughout this semester. But first you have to learn what a limit is and how to work with limits and some properties of limits, and today we're going to start that process. The limit of a function is the value the function wants to be. It's the value the function wants to get to. The function may not get there, but it's the value the function wants to be. Since the function f of x is the same as the y value, the limit you're looking to find is always going to be the y value of a function. If you want a limit, you're looking for the y value. What height does the function want to be at? What y value does the function want to be at? Notation for a limit. Here's notation for a limit. You abbreviate limit as LIN. Underneath, you find the x value you're getting close to, and you put the function up here. This is read as the limit as x approaches 4 of f of x. Meaning, what value does the function want to get to as the x values are getting closer and closer to 4? And we have a graph up here to kind of demonstrate this. Have a parabolic function. So the function, as we're tracing this, and as the x values get closer and closer to 4, as x is getting closer and closer to 4, the function is getting closer and closer to this hole. The limit has to be the same from the left and the right. The function has to want to get to the same point. So as I move to the right, trace the function from the right side, the function is getting closer and closer to that hole. Even though the function is not defined at that hole, the function is defined up here. The limit of the function is the value the function wants to get to. So the limit as x approaches 4 of f of x is going to be 2. It's going to be this y value. The value of the function, f of 4, is 3. But the limit is where the function wants to be. So the limit is the y value the function's trying to get to. There are 3 ways to find the limit of a function. There's a numerical approach, where you basically plug in numbers. There's a graphical approach, similar to what I just did, where you look at the graph and see what's happening. And then there's an analytic approach, where you apply some algebra and you simplify it a little bit and work to an easier function, and you can find the limit there. Today we're going to work with the numerical approach and the graphical approach. Our function is x cubed minus 8 over x minus 2. We want to take the limit as x approaches 2. Now when we plug 2 into this function, you see the denominator is 0. So it's undefined at that point. So it's not as simple as just plugging in and saying the value. So the numerical approach, we make a table of values very close to that x value and see what happens with the y values. So I have x at, I want to get to 2. So I have x at 1.9, 1.99, 1.999. So I'm getting close from the left side of 2. I want to do the same from the right side. I started at 2.1, 2.01, 2.001. Both of those are getting closer and closer to 2. Now we want to see what the y value is as we get closer and closer to 2. At 1.9, you're 11.4, 11.94, 11.994. So these y values are getting closer and closer, it seems like, to 12. From the right side, 12.6, 12.06, 12.006. From the right side, they're also getting closer and closer to 12. So through a numerical approach, we say the limit of this function as x approaches 2 equals 12. The y value is getting closer and closer to 12. Now we have a graphical approach. During a graphical approach, you look at the graph, you look at the picture of the function, and you see what's going on from both sides. Where does the function want to get to from the left? Where does the function want to get to from the right? And the value that they want to be, not necessarily where they're at, is the value of the limit. So I have this function here, a piecewise function that we don't even have definitions for. We just know that this function is f of x. So I have a little parabolic function right here, a linear function right here, and a separate linear function right here. So a three-piece function. I'm going to do two limits right here. I have the limit as x approaches -1 of f of x. You see at -1 this splits from a parabola to a linear function, so that's a common question. Where the piecewise function splits is where you'll be asked about the limit often. So I see what's happening as I come from the left. As I trace this function and come from the left side of 1, closer and closer and closer, I'm going to this point. From the right side of 1, I'm coming this way. Remember, we're looking at the function as both sides approach 1 on the x-axis, so I'm tracing like this, and they both converge on this point. So therefore, the limit as x approaches as x approaches -1, is this value here, the y value, which is -4. Next, we look on the right side. The limit as x approaches +2 of f of x. So again, I want to look what's happening from the left as x is approaching 2, what's happening from the right as x is approaching 2. So I want my points, my x values to converge on 2. From the left side, I'm coming at this point, or the function's coming at this point. From the right side, the function's coming at this hole in the graph. So these functions are approaching different points. What it wants to do from the left side is not what it wants to do from the right side. When that happens, the limit is said to not exist. So you can write does not exist, or you can simply write the initials DNE for does not exist. There are three ways a limit cannot exist or can fail to exist. The first way is one we just talked about. The function approaches different numbers from the left and from the right. Approaches different y values from the left and from the right. So you see from the left here, the function is approaching something up here. From the right, it's approaching something down here. Therefore, it's attacking or coming at different numbers, different y values from both sides. Doesn't matter high, low, close, whatever. If it's not the same exact number, then the function, or the limit is said to not exist. Also, the function approaches positive or negative infinity from either side. So you have a function here. Both sides are going up, and you would have an asymptote in this case. If the function is going up here, you have an asymptote. The function was coming down at an asymptote, or if it was going opposite ways at an asymptote. Either way, if the function is going to positive infinity, negative infinity, or 1 to each direction, the function is the limit of the function again is said to not exist. Finally, if the function oscillates as it gets closer and closer to the x value, the function is said to not exist. You think about a fan that you turn on oscillate, it means it turns back and forth around the room. Well, oscillate in terms of a math graph kind of reminds you of the trig function, where it goes up and down and up and down. Now, what would happen when a function oscillates around the next value is the humps and valleys kind of tighten up around that x value. So they would start wide, and then they start getting tighter and tighter and tighter as you got closer and closer to that x value. That actually the function would be undefined at that x value, but even if you did it on a calculator, it kept zooming in and zooming in and zooming in, you would still see this keep going up and down. And the same would happen on the other side. It would start going up and down real fast, and then slowly spread out to a normal wave function. So three ways a function, or the limit of a function, does not exist. Goes at two different numbers, goes to positive or negative infinity, or oscillates, gets a real tight wave function right around that point, right around that x value.